This is the 2022 Red Bluff High School, NASA, Lassen Volcanic National Park, astrobiology presentation of findings. And so what you're here for today is a presentation by Red Bluff High School students who have worked really, really hard this entire year to study some of what's going on up at Lassen Volcanic National Park. And they've done this under the guidance of some very influential and special NASA scientists. This program has been around for a couple of years now, actually more than a couple, over 10, in one capacity or another at Red Bluff High School. I have been a part of this program since its inception and have really seen it grow from an after-school program to a class that we now offer up to 20 students every single year. And these 20 students get a real unique opportunity to not just learn about science, but to actually go out and do science, which is something that is very it's very interesting to them and very applicable to them, not just this year in their studies, but hopefully later on in life also. Tonight, what we hope to share with you is some of what they did. I would be lying to you if it wasn't a challenge this year based on just situations. As we all know, we are still dealing with the pandemic on one level or another, and the restrictions that has placed on us, both in the school and in the field, has definitely been felt. In addition, Lassen Volcanic National Park last summer was impacted greatly by a wildfire. The Dixie wildfire tore through much of the area of the park that we tend to focus on and perform some of our research in. And that really also impacted some of what we were able to do this year. But as a testament to these students, we persevered, we carried on, and we were able to still get the job done. And you're going to be able to see just how much they were able to learn, how much they were able to actually to study and conclude based on this research that was done under extremely difficult circumstances. Because of that, I couldn't be more proud of this group. And I'm just excited to share with you and for you to have the opportunity today to see exactly what they've done. And so with that being said, I'm going to pause my comments for now, and I'm going to pass it along to Ranger Sweeney. Ranger Kevin Sweeney is our contact with Lassen Volcanic National Park. And he's going to tell you a little bit about how the park is influential and is impacted by this program as well. So Ranger Sweeney.
Well, thank you, Mike or David. And it is really a testament to these students to overcome all of the challenges of both COVID and the Dixie Fire, and still being able to come up and do these field experiences and experiments. This course really emphasized hands-on experiments, and it emphasizes in the field science. It emphasizes hands-on science, which I think is so important, that we get a tangible opportunity for these students to go and connect with the park, connect with science, in addition to working with these wonderful people from NASA who can show that science is a wonderful career and a wonderful opportunity for them. It opens doors that are unimaginable for a lot of folks in Northern California, and to be able to have this opportunity to work with NASA, to work with the National Park Service, to get this kind of exposure, it's just an absolutely incredible experience. Personally, I just had a blast hanging out with you guys in the park, collecting samples. And boy, every time you guys came to the park, it was freezing rain and snowing and just the best, most wonderful weather as we've been going through droughts. So cheers to you. Let's have you guys come up for the rest of the summer if we can, because it seemed like every time you guys came up, we got some big rain or big snow, and you guys persevered through it. I couldn't be more proud of you. And thank you so much for allowing me to be part of it. I really appreciate it. Please know both Red Bluff High School, both the students and the staff, and NASA Ames folks, you guys are something that we're really proud of at Lassen. And I speak for Superintendent Richardson when I say that this program is something that we brag about quite a bit. It really combines all the best aspects of national parks, partnering with our local communities and other government organizations to show that national parks are these living laboratories, not just places to go and set up a tent and relax, which they are certainly that. And it is important that there are those. But as places where we can study and learn about other worlds, learn about other planets, question things that are happening on our own planet, and be curious. And one of my favorite things about this class and about having students come up is it just encourages that critical thinking, that kind of curiosity that is so important in making the world a better place. So Red Bluff High School students, great job this year. I hope your feet have finally dried out, and thanks for all the hard work and perseverance on the great hikes that we did and your frozen fingers collecting samples. Good job, guys, and thank you so much for all your work.
Thank you very much, Ranger Sweeney. It's really been a joy for us to work with you as well. The students have amazing stories that they share just about the time up there, obviously the cold time, but it was a pretty just some very special trips that we had up there. And so thank you for making that happen and making this program such a make us all feel so welcome up there. Right now, I think what I'd like to do is introduce you a little bit to the chat room and just so you know where to ask questions and what to do. And so if you look on this live stream, upper right-hand corner on my tab, right below the tab, it says go live. And below that, there's a little circle that has like a talking arrow in it. And if you click on that, it'll open up a chat. And if you open up that chat, you can then type in things at the bottom of it. And so we'd like to kind of reserve this for questions at this time. And so if questions come up, just go ahead and please enter them into this chat. And we will get to those towards the end of our presentation. But I want to make sure that you're aware of that. So if a question comes up, you can type it in there and just not have to worry about forgetting it type of thing. So anyway, our next speaker tonight is going to be Dr. Dave Desmarais, and he's going to talk to us a little bit about not really Lassen Park, but how the research that's being done up at Lassen Park can be tied to some of the research that's currently being done up on Mars. So he's going to share a little bit about the information as far as the research that's being done up on Mars right now.
Thanks a lot, Dave. Yeah, I'd just like to start by saying that we're just in a golden age of exploration in space, on Mars and beyond, and then all the amazing telescopes, the launch of which is going to just look way back in time and deep into the universe. It's really quite remarkable. And of course, this is all enabled by new technologies that have been developed. And of course, that has really accelerated over the last few decades. And not only does the new technology make it easier to do these missions, but it also allows the public to become much more engaged, actually almost in real time as these missions unfold. And so, because of all of these missions and now just focusing on Mars, because of all we've learned about Mars over the last 20, 30 years, we basically took advantage of this strategy called follow the water. And that is, if you're going to ever have life on Mars, you need the water. And so we were just trying to see, is there any evidence that water was at all abundant in Mars and was sufficient perhaps to support life? And what that succeeded in doing is documenting that, yes, indeed, water really was very widespread, especially on ancient Mars. But it led to sort of a problem, and that is that, or a challenge, I should say, and that is that there's so much evidence of water all over the place. Which of the places should we land? How do we choose between a place that's more promising or places that are less promising? And so for this, we need to do what's called site selection. We need to be very careful about which sites we pick because we don't get very many chances to go to the surface. And for this, then, we have to study these areas in more detail beyond just the water. Are there other things there that could have supported life, which might be the best places that could preserve evidence of it if it was ever there? And so it really invokes a lot of the field work, very advanced field work that people have done on ecology and biology. And some very advanced methods have been developed for our field work on the Earth. But the problem is, of course, the challenges of space flight really cuts down our ability to take advantage of a lot of that. We really have to pare down to a more simple and straightforward and possible approach. But the key thing is that we can still employ strategies that were developed long ago by Earth scientists and that were proven to be very effective with not nearly the technology in terms of observations that you're able to do walking out in the field yourself. And so these are sort of time-honored exploration strategies, and then starting with, for example, doing reconnaissance of a field area to grasp sort of the geographic context and to develop initial impressions about what went on there in terms of also the potential to support life. Secondly, then you visit certain key locations to make additional observations and take samples, which allow us to maybe start formulating hypotheses about what occurred there. And then, of course, you come back to the lab, you analyze the samples, you do experiments in the lab to try to test these hypotheses, see if your experiments can give you more insight about what's going on there. And then, of course, very importantly, you have to write up your results. You have to put them into the scientific literature. And also you give oral presentations in order to, disseminate that to a wider audience and to get very important feedback. Now, the interesting thing is that this course in astrobiology at Lassen, at Red Bluff High School, that's the structure of the course. What I just described to you is these steps that we do as fundamental scientific approach, and it's the backbone of how we do science exploration on these missions. That's the template for this course. And we have selected a couple of several sites up in Lassen, particularly in the Sulphur Works area and Warner Valley area, because they provide sort of modern and accessible sites that resemble very promising sites on Mars. They share many of the features that we think might have been active features long ago on Mars. And so as a result of this, these students have really gained a perspective about our approach to Mars and the basic challenge, and that is, given an environment, can life exist there? And if it does, what kind of life would there be there? So this environment-life connection is what this course really stresses. And that's exactly the strategy that we need in order to determine which sites to select on Mars and then what to do when we get there. What do we measure? And so in a way, the achievements of this class and the perspectives they've gained has developed critical thinking skills and also just, basically analytical skills, which I think will serve them very well. And of course, NASA has a vested interest in this because ultimately this next generation is going to take ownership of space exploration. And for that matter, many of the other things that are so important for our society down the road. So thank you very much. Look forward to seeing this year's version, and let's proceed.
Thank you, Dave, very much. And as Dave pointed out, we are very interested in certain areas of Lassen Park. And if you remember, I said earlier how impacted we were in even getting to these areas. And who you're going to hear from next are the interns and their research. But I'd like to just kind of set the foundation for this a little bit and talk a little bit about some of the challenges that we faced. We do follow the scientific method. That's what this entire class, this entire program is based on, identifying a problem. And then once we identify it, try to come up with a solution and then conduct some experiments that help us to kind of better understand those solutions. And then try to go back then and see, was our interpretation of this problem correct? That's easier to do if you can actually fully get your hands on the problem and fully experience it. This year, we tasked these students in looking at some of these sites, some of these very interesting, important sites of Lassen Park without the ability to get there. We were able to substitute other sites for this, but in the end, it became just I don't want to, it wasn't impossible, don't get me wrong, but it became difficult for them. And so I am very, very excited to share with you what they came up with, what they were able to discover, while overcoming just the challenges of the situation that they were dealing with. And so with that being said, I'm just going to kind of let this go. They have come up with a presentation now that basically explains beginning to end all of the research and work that they did this year. And so feel free to just kind of follow along. And if there's questions that come up, I told you where that chat window is. Feel free to type those questions in and we will address them once the presentation is over. So thank you.
Hello, everyone, and welcome to our cumulative presentation for the 2021-2022 NASA Astrobiology Internship Program. I am Cameron Beeman, second year in the program, and I will be the Master of Ceremonies tonight. This program is a collaborative effort between Lassen Volcanic National Park, NASA's Ames Research Center, and Red Bluff High School to go beyond standard science classes and provide a unique learning experience. Tonight, we will be reviewing all that we have done in the program this year. To start us off, Olivia Palangoni will go over our outline for the night.
In this presentation, each intern will be explaining the key parts of our study and how they are interconnected. To begin, the concept of astrobiology will be explained and why Lassen Volcanic National Park is a part of our studies. Then the matter in which we collected samples will be explained. Next, each field site we studied will be described. Then the rock dissolution experiments we conducted in the classroom will also be outlined, along with the experimental parameters of our Winogrossi incubations. Lastly, the second-year interns will summarize the water chemistry at each site. Next, Hiram Bliss will be explaining what astrobiology is.
Astrobiology is the investigation of the origins, distribution, and future of life in the universe. A key aspect of astrobiology is to search for and characterize the full diversity of habitable environments, both on early Earth and on other planets. Volcanic activity and its interactions with water are key aspects of ancient habitable environments on Earth. Evidence of such interactions have been discovered on Mars, and these interactions probably also occurred on other Earth-like planets in the universe. And now Asael Diaz will be explaining why we are so interested specifically in the Lassen Volcanic National Park area.
Volcanic activity and its interactions with water were key components in allowing past life to live in their environment on Earth. From photographic evidence taken by our fellow robotic friends on Mars, we know that Lassen Volcanic National Park shares various geographical similarities with Mars. This being the aforementioned volcanic influence and effects of liquid erosion on the ground. The volcanoes in Lassen Volcanic National Park create unique opportunities for study. For example, groundwater in Lassen Volcanic National Park interacts with molten rock stemming from volcanoes. The subsequent groundwater, now altered by its previous contact, interacts with living organisms, microbes, and landscapes of its surrounding environment. Seeking to understand the mechanisms behind Lassen's wide range of environmental conditions and rich microbial life that are all impacted by the volcanic activity, we can replicate many of the hypothesized conditions of early Mars. The study of microbes in the present day can help answer the question, was there life on Mars? Up next, Todd will talk about the prerequisites for life to even exist.
In our studies of Lassen, we looked not only at the conditions of the water chemistry and geology, but also at the microbial life that is present. There are 4 categories that we observed to determine if the conditions are favorable for life to survive and prosper. The first of these 4 requirements is for life to have a solvent present. A solvent, typically that of water, is necessary in order to dissolve many nutrients for life. These essential elements for life which are dissolved by water include carbon, hydrogen, nitrogen, sulfur, and more. For life to be present in an ecosystem, a source of energy also must be present. Energy is provided to the organisms at these sites through the processes of photosynthesis, the absorption of light, and chemosynthesis, which provides energy through chemical reactions. The fourth and final necessity for life to exist is that of favorable conditions in terms of temperature, pH, and salinity. For life to exist, the conditions of the environment must be suited to what the microbes need. Many microbes have different adaptations to survive in different environments. For instance, many organisms can survive in an acidic environment, while others must be in a more neutral environment. On the whole, it is necessary for the 4 categories seen in the Venn diagram to be present for life to survive and grow. Now, Cameron will introduce the field sites that we studied at Lassen.
After learning about astrobiology and the requirements for life, we looked for field sites within Lassen Volcanic National Park to see if we could apply what we had learned. When observing Lassen, it is important to remember its history. Lassen Volcanic National Park once had an ancient volcano, named Mount Tehama. Over time, Mount Tehama eroded away from the inside because of the underground acidic hydrothermal activity, causing it to collapse in on itself. This volcano was massive, its footprint outlined in red. Within the remains of this ancient volcano, we see the Sulphurworks area circled in yellow. At Sulphurworks, we picked 3 significant field sites to observe: Ridge Lake Stream, Upper Pond, and Big Boiler. Now moving outside of the volcano, we see the Warner Valley area. Within Warner Valley, we picked 2 significant sites to observe: Paddlewell Creek and Alkaline Spring. We will now hear 5 of our first-year interns describe the field sites we observed in Lassen Volcanic National Park. First, we will hear from Mia Gleason.
Paddlewheel Creek is found in the Warner Valley area of Lassen Volcanic National Park. Paddlewheel Creek is a freshwater stream with conditions that can commonly be found at any other national park because they are moderate and relatively normal. When you approach Paddlewheel Creek, it appears to be a typical mountain stream that is thriving with an abundance of life. There is grass and trees to the edge of the stream, as can be seen in the photo, along with algae in the stream. The temperature and pH support this because the temperature at Paddlewheel Creek is 9 Celsius, which is an average temperature, and a pH of 6.7, which is neutral. The conductivity of Paddlewheel Creek is 52 microsiemens. There is no volcanic activity at the site because it is a freshwater stream. Up next, Natalie Moore will be introducing Ridge Lake Streams.
Ridge Lake Streams of Sulphurworks appears to be a typical mountain stream. It is fed by runoff from Ridge Lakes in Lassen Volcanic National Park. However, the water chemistry here tells a different story. The pH of 5.8 seems standard, but is low in comparison to places like Paddlewell Creek, making it slightly more acidic than that site. The conductivity of 290 is relatively high when compared as well. The stream is filled with lots of vegetation and algae. And now I'm introducing Courtney White to talk about Sulphurworks Upper Site.
Sulphurworks Upper Site is a hydrothermal feature at Lassen Volcanic National Park. Upper Site is a small acidic pool adjacent to Ridge Lake Stream with a low pH and a mild temperature. Upper Site has a temperature of 10 degrees Celsius or 50 degrees Fahrenheit and a pH value of 3.6. The pool appears to be bubbling, and the reek of sulfur can be smelled when approaching the pool. As seen in the top right image, Upper Site has a beautiful vibrant top layer of green photosynthetic microbes. When removing the top layer of green microbes, a reddish-purple microbe layer can be observed below the green surface.
One iconic hydrothermal area found at Lassen is the Big Boiler found at Sulphurworks. When approaching the site, you'll notice the yellow-orange clay hillside surrounding the area and see little to no vegetation like plants or shrubs growing around. It also has a strong distinct smell of rotten eggs, which is sulfur, and has boiling mudclouds up close. Big Boiler has a high temperature of 107 degrees Fahrenheit found inside and an acidic pH concentration of 3, making the highest in all the field sites. This is because the groundwater reaches to a boil, causing the water to bubble and steam. The next site being talked about is Warner Valley Alkaline by Maya Rodriguez.
At first glance, the alkaline site in Warner Valley seemed to be a healthy stream, much like Paddlewell Creek. However, looking closer, we saw it was much different. In these pictures, you could see a thermal image of the heat coming from the water, that there was steam coming off the water, little to no plant life, weathered rocks surrounding the stream, and thick green micromats, along with a few dead insects in the stream. Additionally, it has a temperature of 62 degrees Celsius, or 144 degrees Fahrenheit, a pH of 6.6, and a conductivity level of 1010. Together, this indicated a much different environment at the alkaline site than we have encountered in Lassen Volcanic National Park.
After viewing the field sites, we returned with questions regarding the various readings we took and observations we made. Why did we see the various differences in pH and temperature? And why did we observe differences in the life at each site? We set up several experiments to explain these differences. Now, Leah Moreno will give us a brief introduction to the lab environment and tools we used.
Using the meters shown, pH, conductivity, and temperature were measured from each site. pH is a measurement of acidity from 0 to 14. Sites at Lassen Volcanic National Park range between the acidic levels of 1.7 and 7. Conductivity is a measurement of the dissolved solids known as ions. Cations are positively charged and anions are negative. Sulfate is an anion we've measured from the sites produced when the volcanic gas hydrogen sulfide reacts with oxygen and water. This creates the acid that contributes to the acidity of sites and indicates the presence of volcanic activity.
We will now hear two of our first-year interns describe and discuss our findings from the water chemistry experiments we conducted in the lab. These experiments were designed to explain the interactions between rock and water of various pH and temperature values. First, we will hear from John Sheffield, who will be discussing the effect rock has on the pH of a solution.
During our visitations at the Lassen Volcanic National Park field sites, we were presented with a question of how the pH at these different field sites will react with the rocks surrounding them. Our hypothesis for this question was that the pH of these field sites were dissolving the rock into the water, which raised the pH. To test our hypothesis, we set up 6 different testing stations that fluctuated in both pH and temperature. We then used the 2 rocks found in abundance near the Lassen Volcanic National Park field sites as rock powder. The data below shows that over our month-long experiment, we had to continually add sulfuric acid to the solution to lower the pH down to the desired pH. This can be seen in each line, with the green line needing 3,200 micromoles of sulfuric acid over 30 days to lower to the original pH, and the red line needing 9,700 micromoles. When observing the yellow and blue line, the pH of both is 5.5, which is closer to a neutral pH of 7. This results in their pH raising a much smaller amount each week when compared to the solutions with a pH of 2. Therefore, from these experiments, we can conclude that rock reacting with an acidic solution will raise the acidic solution's pH. I will now be introducing Aubrey Norton, who is presenting solubility of rock at different pH and temperatures.
We compared the change of net conductivity in experiments that have like pHs and different temperatures. We know that any difference in conductivity between the 2 experiments must be because of the change in temperature, because that is the only difference. The same goes for having like temperatures and different pHs. Net conductivity is the total amount of rock dissolved into solution during an experiment. We hypothesized the solutions with a lower pH were able to dissolve more rock into solution than that of a higher pH. We were able to test this through 2 experiments. One experiment had a pH of 2 and the other had a pH of 5, and both were at the same constant temperature. Our data shows that in fact the lower pH was able to dissolve more rock into solution. Our next hypothesis was that solutions with a higher temperature were able to dissolve more rock into solution than that of a lower temperature. We were able to test this through 2 experiments. One experiment had a temperature of 35 degrees Celsius, the other had a temperature of 20 degrees Celsius, and both were at the same constant pH. Our data shows that in fact the higher temperature was able to dissolve more rock into solution.
We will now hear 4 of our first-year interns describe and discuss our findings from the microbial incubations we conducted in the lab. These experiments were designed to explain and explore the effect of altering the various variables of a microbe's environment. First, we will hear from Sierra Lim on the effect of altering light.
We tested the impact of changing the color on microbes to see how much of the microbial life and diversity would be affected. To test this, microbes from the big boiler and alkyne sites were put into a container that only allowed blue light to transit through. This experiment gives us a better understanding on which microbes can survive in temperature-changing climates, which correlates to the past life on Mars. After examination, growth of the microbes was inhibited by the lack of light and energy that is typically provided primarily from red or orange color waves, which are being filtered out. However, some microbes were able to survive and be unaffected by the change, as they were more heavily rely on the blue light that was still present in the system, unlike some microbes that needed the red or orange light to prosper.
When we gathered the microbes from Lassen Volcanic National Park, we tested the microbes' ability to adapt to different environments. One of these environmental changes was the effects of temperature. We created 2 different Winograzi columns to determine this effect. The first column was the control and the second was the experimental. The control was kept at room temperature, registering at 74 degrees Fahrenheit. The experiment was kept in an incubator, registering at 105 degrees Fahrenheit. For the next 2 months, we observed any physical change to our columns. The first two pictures show the control of the experiment. The one on the left is the Winnicott column, and the one on the right is the microbes under a microscope. You can see the biomass of the community is strong, and there are different types of microbes, which show that there's a high amount of biodiversity. The pictures on the bottom show the experimental column. Under the microscope, we can see that biodiversity is lacking. As you can see, the change is drastically different. The biomass of the community has greatly decreased, as well as the biodiversity. After the 2-month observation period, we concluded that when the temperature was either raised or lowered from the original temperature of the field sites, it would negatively affect the microbes both in biomass and in biodiversity. Now that we covered the effect of temperature on the microbes, Russ and Vaught will introduce the effects of pH.
After our visit to Lassen Volcanic National Park, we wanted to determine the extent of environmental changes these microbes can handle. We tested how pH would affect these microbes. Our initial hypothesis was that a change in pH in a microbe's environment would visually change their growth in abundance and diversity. During the experiment, we checked the pH of the control and experimental every Friday for the next 2 months. After experimenting, we determined that the original showed optimal growth in biomass and biodiversity, while the experimental showed little growth in biomass and biodiversity, resulting in us to believe that an increase or decrease in pH negatively affects the microbes in all aspects of life, as shown by the reduction of biodiversity and biomass. Now we will talk about the effects of change in concentration on the microbes.
Solute concentration, otherwise referred to as conductivity, is a measure of ions dissolved in solution. These ions are utilized by microbes as a source of nutrients or a fertilizer. Field sites in Lassen Volcanic National Park had a variety of ions dissolved in solution and a broad range of conductivity values. Certain microbes have specially evolved to survive in a specific set or threshold of conditions and have a threshold of solute concentrations that they can survive in. Our general hypothesis for lab experimentation was that a decrease in conductivity would lead to a decrease in microbial activity and vice versa, depending on the magnitude of the change. However, lab experimentation provided inconclusive results, as no apparent correlation between solute concentration and microbe activity could be found. Pictures of these lab cultures can be observed to the right, with the number of days, magnitude of change, and field site indicated.
Earlier, we had questions on why the various field sites had differences in pH, conductivity, and microbial life. After conducting our experiments and compiling our results, we now have answers to those questions. We have gained a new understanding of how Lassen Volcanic National Park works, and we feel confident that we can share that understanding with you. Now, you will hear all 5 of the second-year interns interpret the field sites with our new understanding.
As mentioned earlier, Paddlewheel Creek is a typical mountain stream that exists as snowmelt and rainfall flows through the valley. The pH of rainwater is around 5, while the pH of the stream is around 6.7. This change in pH is explained by our rock dissolution experiments, where we prove that the pH of a solution increases over time as rock is dissolved within it. We also saw in our rock dissolution experiments that environments with a neutral pH and cold temperature dissolve rock but at a fairly slow rate, which explains why the conductivity is so low and why there was not a large increase in pH from the original, as only a small amount of solutes were dissolved. Paddlewheel Creek also contains an extremely low level of sulfate, which is because of the lack of hydrothermal input seen at the site, once again confirming the simplicity of the creek. The microbes at Paddlewheel Creek, which primarily consist of a green algae, are able to survive and grow due to the mild conditions they live in. In the biology experiments previously discussed, these conditions of a neutral pH and cold temperature allow for steady growth, and a variety of diverse microbes are seen when these conditions are mimicked. Now, Asael will discuss the water chemistry found at the Ridge Lake stream of Sulphur Works.
The Ridge Lake stream resembles very much the image of Paddlewheel Creek, that of a typical mountain stream. Its main source is runoff from snowmelt and rainfall, and its low temperature of 40 degrees Fahrenheit is indicative of the cold climate typically seen. While the pH of Ridge Lake was measured at 5.8, we can assume that its actual pH would be closer to that of Paddlewheel Creek when accounting for the pH change from the snowstorm during our measurements. This is because, as stated before, our rock dissolution experiments indicated a rise in pH when rock dissolved within water, just like Paddlewheel. However, deviations start to appear when talking about conductivity and sulfate levels. Contrary to Paddlewheel's conductivity of only 52 microsiemens, Ridge Lake was at a low to moderate level of 290 microsiemens. Likewise, Rich Lake had a relatively higher level of sulfate of 1,260 micromoles when compared to Paddle Wheel Creek. As seen in our rock dissolution experiments, high levels of sulfate were suggestive of hydrothermal influence present within the Rich Lake stream, indicating some sort of volcanic activity feeding into it. The presence of hydrothermal activity helps explain the estranged conductivity, where the solids from the source of the hydrothermal activity flowed into the stream to increase the conductivity to such a level. However, we are unsure if the sulfate comes from a vent directly connected to the stream or runoff from another site. Regarding the biology of Rich Lake stream, there seems to be a relative amount of microbes subsisting well in their environment despite the higher than usual sulfate level. As seen in our microbe experiments, the moderate conductivity levels and neutral pH allows for steady and abundant growth. Up next is Cameron to discuss Upper Site.
The Sulphurworks Upper Pond is a field site with clear hydrothermal input. Here we saw bubbling in the pond, which one could assume means it had an elevated temperature. However, the pond had a cool temperature of 10 degrees Celsius, or 50 degrees Fahrenheit. This low temperature means that the bubbling is not a result of high temperature. We then can assume that this bubbling is a result of the release of volcanic gases. The pond had a relatively high sulfate level of 2010, and, as we already discussed, the high sulfate level is a result of volcanic gases, specifically hydrogen sulfide. This gas is a clear indication of hydrothermal input. The pond also had a low pH of 3.6. This is yet another indicator of hydrothermal activity, the low pH resulting from the present sulfuric acid. The upper pond also had a low to moderate conductivity of 385 microsiemens. This is consistent with our rock dissolution experiment, the low pH of 3.6 being more effective at dissolving rock. Despite the low pH, the upper pond is abundant in microbial life. One can visually see this by the distinct and vibrant green hue of the pond. However, these microbes are visually different from the microbes we saw at Paddle Wheel Creek, meaning the differences in water chemistry has influenced the microbial communities. Now, Hiram Bliss will describe to us the Sulphurworks Big Boiler site.
Seeing Big Boiler, it is a large pool of bubbling and hot mud. You can smell the distinct sulfur smell up close and easily see how volcanic the site is. As you can see, the mud pot has been practically carved into the hillside over time from the acidic environment and the hydrothermal activity. The reactions and conditions have altered the entire environment of that area, digging the hole of the mud pot, melting all the snow around the site, and creating that smell of sulfur. The sensory evidence, along with the sulfate level being so much higher than other sites, provide evidence of how hydrothermal activity is very active in Big Boiler. Despite the interactions Big Boiler has between rocks and water, like John spoke about earlier, as you can see, the pH is still pretty low due to the constant and active hydrothermal activity and the acidic environment that is keeping the pH as low as it is. Due to the low pH and the high temperature created by the hydrothermal activity, both of which work to increase the reaction rate and efficacy of the chemical reactions, Big Boiler has a really high conductivity, similar to what we would expect based on our rock dissolution experiments. High temperature and the low pH make solutions a lot better at reacting with the rocks. As evidence of this, at Big Boiler you can see the conductivity is so high, especially compared to the other sites like Paddle Wheel Creek that have more ambient temperatures and closer to neutral pH values. Another byproduct of Big Boiler being in this incredibly acidic and extreme environment and having a high temperature is the small amount of life around and in the mud pot. The microbes here consist of extremophiles, which are extremely tolerant microbes. This is because these microbes are the only life that are able to live in Big Boiler's intense environment. The high temperature and low pH make the conditions too harsh and inhospitable for most things to survive. Similar to how only a small amount of microbes can live in Big Boiler, we saw in our biology experiments that microbes in extremely high temperatures did not grow very well or died. Olivia will now explain the water chemistry and biological environment of our alkaline site.
As stated previously in the presentation, the alkaline site is a stream that runs through Warner Valley. Peering into the steaming water, one can observe that there are thick mats of green biomass. Water samples taken from the site indicate that the temperature of the water is 62 degrees Celsius or about 150 degrees Fahrenheit, and the amount of solutes dissolved in the spring is 1,010 microsiemens. The most shocking fact about the spring is that the pH recorded at the site is 6.6. This pH has about the same neutrality as bottled water. From our rock dissolution experiment, we hypothesized that solutions sitting at a high temperature would dissolve more solutes, which was proven to be correct. The high temperature at the site is the explaining factor into why the solute concentration is so high. The sulfate concentration of 1,690 micromoles and the high temperature indicate that there is hydrothermal output. A high conductivity and high sulfate levels is what would be typically recorded at a site with hydrothermal output. What makes the alkaline site so unique is that the pH is neutral, in contrast to sites like Big Boiler and Upper Pond. This can be explained in our rock dissolution experiment. As John stated earlier in our first hypothesis, as acid interacts with rocks, it raises the pH over long periods of time. For thousands of years, the water has been interacting with the rocks, raising the pH. This high pH is what allows the thick green mats of microbes to flourish, even under such high temperatures, which over time the microbes have evolved to be specifically adapted to withstand the heat. Lastly, Cameron Beeman will be explaining the significance of our studies.
Lassen Volcanic National Park is an example of how hydrothermal activity occurs on Earth and can sustain life in microbial communities. The discovery of ancient hydrothermal deposits on Mars indicates that some Martian environments might have sustained life in the past. The research at Lassen enhances our ability to search for and characterize any life that might have existed on ancient Mars. With that, we will conclude our presentation and move into a special portion of the night. To show our appreciation for the program and all involved, my fellow interns and I have prepared what we call impact statements. I will start us off. In case you missed it, my name is Cameron Beeman, and this has been my second year in the program. I have loved my time in the internship because of my love for science and learning, of which there was no short supply during my 2 years. Also, the opportunity to work with and learn from NASA scientists is phenomenal and completely unique to Red Bluff High School. I am grateful for the effort of the scientists, Lassen Volcanic National Park, and Mr. Michael for making this program possible.
Hi, my name is Todd Bell, and I have been an intern for this program over the last 2 years. And having taken this opportunity and working alongside these NASA scientists, conducting fieldwork and learning whatever I could from them that I would have never experienced otherwise, has had a huge impact in preparing myself for my studies after high school and becoming a more well-rounded student for the future.
I feel a great amount of appreciation for how Mr. Michael and the NASA scientists helped me to improve my knowledge of real experimentation and for how they've taught me to analyze and understand the environment around me.
My name is Olivia Palanconi, and I've been an intern in this program for the past 2 years. It has truly been a once-in-a-lifetime opportunity, and I'm so thankful for all that I've learned under the help of Mr. Michael and the NASA scientists. This program has really helped me solidify my passion for the STEM field, and I'm truly thankful for that. Thank you.
Hello, I am Asa Diaz, and thank you for watching our presentation that we all have worked hard for the last 2 years. It wouldn't have been possible without the grueling but very satisfactory education provided by Mr. DeMarais, Mrs. Parenteau, and Mr. Cuba. And thank you, Mr. Michael, for the supportive and very persevering attitude you had with us. I hope to get in my brain the mindset of a logical but empathetic person, like the way you guys showed us. Thank you.
Hi, my name is Ryan Wynn, and this is my first year in the NASA internship program. This program gave me valuable insight to what college-level studies entail by allowing me access to field sites that weren't open to the public to actually scoop for microbial life, which put me directly into the shoes of an actual scientist, which was pretty cool. It taught me many things that you really can't learn in your average science class, and studying next to real NASA scientists was an honor, and I'm truly grateful for that.
My name is Natalie Moore, and I'm a first-year intern, and the NASA program has provided me with a more hands-on experience and learning in a way that I've never experienced before. I'm very happy to be a part of it.
My name is John Sheffield. I'm a first-year intern in this NASA internship program. This program has taught me so much and allowed for a hands-on approach to science. For this, I thank all the NASA scientists and Mr. Michael for allowing such an amazing opportunity at Red Bluff High School.
My name is Leah Marino, and I've been in the NASA internship program for the last year. This program has reminded me of the interests I had in space as a kid and given me the ability to understand the requirements for microbial life I hadn't known of before. It was an honor having the chance to be part of this, and I really appreciate all the time put into our learning by the NASA scientists and Mr. Michael.
Hi, my name is Sierra Lim, and I'm a first-year NASA intern. Throughout this program, I have learned so much about astrobiology and the importance of life. I was privileged enough to work with the most amazing scientists throughout this whole year. Through the in-person experiments and the live Zooms, I was able to get an experience I would have never got anywhere else.
Hi, my name is Courtney White, and I'm a first-year NASA intern. This program is an amazing opportunity and has turned my love for science and space into an obsession. Since I was a kid, I have been very inquisitive about life, the universe, and how everything came to be. I want to know everything about everything. This program has allowed me to understand the biological, chemical, geological, and hydrothermal interactions that facilitate the conditions needed for life. I plan to study biochem in college to become an astrobiologist.
My name is Mia Gleason, and I'm a first-year intern. Through this internship, I got the unique opportunity of learning more in depth about Lassen Volcanic National Park. I was also able to connect with what we were learning in class with what we saw happening in Lassen.
Hi, my name is Maya Rodriguez, and I'm a first-year NASA intern. This program has exposed me to new things that I've never been exposed to in any of my other classes. Working with the NASA scientists has been a very enjoyable experience, as well as going to Lassen Volcanic National Park and seeing new sights that I've never seen before. Altogether, this is a one-in-a-lifetime opportunity, and I'm so glad that I got to experience this program.
My name is Mauricio Tamayo, and this is my first year of being in a NASA internship program. This program made me regain my knowledge of learning more about astrobiology. When I was younger, I remember being obsessed with space and learning more about basic biology in my elementary school. I always enjoy learning about science-related topics because I always learn something new along the way. And during this program, I learned that every little thing matters in our environment, no matter it's a big or small change. I hope later on in the future I get to learn more about our environment and our impacts.
Hi, my name is Justin Vaughn, and I'm a first-year NASA intern. This program has taught me more than I could imagine. I had a fantastic experience collecting and growing microbes from Lassen Volcanic National Park. I also really enjoyed working with the NASA scientists and learning new things from them. And I would like to thank Mr. Michael for allowing me to be a part of this program.
Hi, my name is Aubrey Norton, and this has been my first year in the NASA internship program. This program has benefited me in multiple ways, with the foremost being with the hands-on experience that it was able to provide. Instead of just being told what was done, I actually got to do it, and this has helped me build a great foundation for continuing science in future careers. Beyond that, discovering what will help and hurt life has just been really fascinating to learn.
Well, great job, interns. Really, really impressed with what you guys just put out there. I know all the hard work that you put into it. I was able to see that firsthand on a daily basis, and I'm sure as the audience was hearing this, there's quite possibly some questions out there, and so I'd like to give the audience a chance to ask those questions right now. So I guess if there are any questions for really anybody involved here, Dr. Desmarais, or anybody else, we'll just open it up to the chat and we'll see what comes up.
Yeah, we have a first question here. I guess this is open to any students who want to answer. This is from Chris. He says, awesome presentations. Wondering if anyone prefers lab work over field work.
Mr. Michael, I think you might have to choose someone.
Well. This is isn't this an interesting predicament I'm in? I'll let you all decide. How about second year interns first? So what second year intern would like to speak for for the other 4 here. So we have 5 second-year interns. Anybody interested in giving your perspective on this first?
I can. So when it comes down to the 2 different types of basically experimentation, field work versus lab work are both very interesting in their own ways. It's very cool to get the experience, but honestly, being able to do field work and then apply it to the lab was awesome. So I prefer field work because it's more hands-on, and I'm a more hands-on type of person.
Thank you, Cameron. Any of the other second-year interns want to chip in, or should I open it up to the first years now?
If I can talk about it, I'd be more than glad to. So for me, I liked actually like the lab work better because I got to work with measurements that Leah talked about. Those measurements I didn't even know before the NASA class, and I really appreciated the amount of like work actual NASA scientists had to go through, like the grueling experimentation and the lab methods. It makes you think about what type of achievements we've made through process instead of like one-time achievements that we just came up with magically. It's a really grueling process, but it's really worth the wait.
Thank you, Asiel. Thank you, Cameron, for your response also. Any first-year interns want to answer this? So what do you prefer, field work or lab work? What do you think?
For me, it was most definitely field work because it was more fun to like work in the go out and like explore and like learn like what actual scientists do rather than like just sit in a lab, take measurements. For me, because when you're out, you could actually like understand what you're doing, and also you like make more memories that way too. Like when we went to Lassen, it was like super cool, and yeah, it was miserable, but it was like I'm always gonna like memorize like that moment because it was just like fun and like it's a learning experience that you literally can't learn like in a lab. So for me, it was most definitely like field work.
Thank you, Ryan. Anybody else before we move on? I see there's a couple other questions. So. Okay, let's move on to the next question then. So it looks like asking about wildfires. Did the wildfires have any noticeable change in conductivity or pH from years past? There was definitely some significant burning, especially around in the Warner Valley area. So around the Alkaline site and around the Paddle Creek sites. I'm going to let Nikki and Mike and Dave address this due to tree dangers, the risk of tree falls and stuff like that. We were not allowed to go into the Warner Valley region this year, but Nikki and Mike and Dave were able to actually go in there being escorted by Ranger Sweeney. And so the three of them have a little bit better feel for this and might have a little bit better perspective than what the interns do or what I do.
I'll just make a couple quick comments. This is Dave. A lot of the water in the sites represents a source that develops over several years, and so the fire just being a month or two before really didn't have too much of an effect. Another effect of a fire, of course, is to increase runoff. But again, this was all during the dry season, so runoff didn't have a chance to have an effect. That said, it's going to be interesting to see next year what the chemistry is like, because then we'll have had a wet season and snow and all of that, and see if that makes a difference. That's it.
Just to add to what Dave said, by monitoring the temperature and pH and water chemistry of these sites, it's actually a great way to track the impact of the drought, because that actually really affects the concentration of these elements in solution. So there's, wide-ranging applications of the work and the measurements that the students are doing. Kevin, I see you.
This is a long-term study, really. I mean, Mr. Michael said that we've been doing this for over 10 years. And so the students, we're really building up a nice database on the effective climate and annual changes.
Yeah, I just wanted to add into that fire is a natural occurring system in this landscape. And so when we have unnaturally suppressed this naturally occurring process for over 40, if not 50 years, we've actually done a bit to chemically change that environment through putting these fires out. Not to say that, a massive 1 million acre fire is something we want to encourage, but I do want to lean into the fact that, what we're seeing and what we had been observing in a lot of these places was an environment that excluded something that is very natural and very the environment's used to having. So, the Dixie Fire is certainly tragic in the fact that it burned up chunks of communities, and in Greenville that story is awful. And in California, we're living with these horrendous mega fires. That being said, as somebody who defends natural processes, I think it's important that we do look at, what is supposed to be occurring in these landscapes, and fire is part of it. And, as we hopefully become more in tune with some of these processes, we'll learn to live on that landscape. So while the fire will impact short-term measurements, I think it's important to know that for thousands, if not millions of years, this landscape has experienced many, many, many fire.
Well, thank you. I'm not seeing any other questions come up right now. And so I don't know if there's any final questions. I'll give you a couple, maybe 30 seconds, a minute or so, and then we'll move on to finish up the program here. I guess one thing that I failed to mention that did come up in the student presentation and definitely in their impact statements was simply how big of an opportunity a program is like this to be able to do field work, to be able to do hands-on work, and not just reading stuff or being told stuff in a lecture format or out of a textbook. And so there's really a uniqueness to this program that I think you heard from the students when they talked about their impact statements and stated that as the leaders of this program, I think we're all very, very proud of. And so, just thank you for that.
Can I make a quick comment?
By all means.
A number of things happened that were unexpected, and guess what? Science has to cope with the unexpected. In fact, missions, sometimes we experience things that we really didn't anticipate, and engineers, and particularly engineers, really have proven to be quite resilient. And just having the challenges that we did this year it quite frankly gives us almost a clearer view of what research is. You have to cope with unexpected stuff and make adjustments. So in that sense, it was a better simulation of the real world than the perfect year that goes according to plan.
There is one of those. I'm still waiting for that perfect year. And so once it comes along, I'll know what I can compare this to, I guess. Anyway, I think we're going to move on to kind of the final part of the program. This is a chance where we have to honor these interns for their hard work. This is a volunteer class. It's an elective class. It's not something these students have to do, and they you can see all the time and the effort that they put into it. And so we do want to acknowledge that hard work right now. And so I'm going to hand things over to Mike Kubo, and he's going to be introducing and recognizing all of the student interns this year.
Thanks, Mr. Michael. Hi, everybody. My name is Mike Kubo, and I'm a colleague of Dr. Demeray and Dr. Prontos at NASA Ames. And this is the part of the presentation the part of the night where we like to recognize and honor all of the participants and partners in this program. And we'll start by recognizing the students. And at the end of every year, we print these, basically it's like the graduation certificate for all of the students. And Mike T, if you wouldn't mind pulling up an example of one of those, what I'm gonna do is I'm going to show you show the audience the certificate, read the text to you, and then I will read all the names of the interns that participated. So as you can see, the certificate says Lassen Volcanic National Park, Red Bluff High School, and the NASA Ames Research Center Astrobiology team take pride in presenting this Astrobiology Student Intern Program Award to, and our first student is going to be Mia Gleason, on May 23rd, 2022, for your outstanding performance, commitment, and dedication in support of the partnership between Lassen Volcanic National Park, NASA Ames Research Center, and Red Bluff High School in the collection of scientific data through laboratory and field work. This work has increased our understanding of Lassen in ways that will enhance astrobiology, as well as the mission of the National Aeronautics and Space Administration and the National Park Service. So I'll go ahead and read all the names of the first year students just to recognize their contribution. So first year interns, we have Mia Gleason, Samuel Groom, Sierra Lim, Natalie Moore, Leah Moreno, Ryan Wen, Aubrey Norton, Maya Rodriguez, John Sheffield, Mauricio Tamayo Perez, Rustin Vaught, and Courtney White. And I want to congratulate you all on a job very well done. It's been a pleasure working with all of you, and we hope to see a few of you back next year. For the second year interns, so, in case this wasn't really highlighted, we do have a handful of students that return every year, and they essentially become team leaders and kind of mentors for the first year interns. And every year when we do this presentation and when we do this class in general, the success of the program and the understanding of the content by the first year interns is generally a sign of how great a job the second year interns have done in their mentorship. And I just want to really acknowledge how fantastic of a presentation you all gave tonight. And I'll really tip my hat to the second year interns for your leadership on that. So nice job, everybody. So the first second year intern that I'd like to acknowledge is Cameron Beeman. Cameron, fantastic job. Thank you so much for participating in the program and for your leadership this year. Second year intern is Todd Bell. Todd, fantastic, really nice job as well. Thank you so much. And it was great working with you these last 2 years. The third person I'd like to acknowledge is Hiram Bliss. Hiram, great job again, fantastic. And you all have a lot to be proud of. Thank you. Next is Asael Diaz. Asael, it's been another great year and really fantastic working with you. Thank you so much for participating and for coming back a second year. And lastly, we have Olivia Pelanconi. Again, Olivia, great job. Thank you so much. And it was really wonderful working with you these past 2 years. So next, I'd like to also acknowledge our partners at Red Bluff and Lassen Volcanic. We always offer, issue a certificate for them as well because they are, equal parts in this process and in this program. So first, I'd like to acknowledge Ranger Kevin Sweeney. Kevin, thank you so much for everything you've done to help support this program. We know you're a big part of its success and your advocacy at the park. Thank you so much. We couldn't do it without you, and we love being a part of the program with you. Thank you so much. And last is, of course, Dave Michael. Again, same thing. We couldn't do this without you. You have put up with us for now over a decade, and we're always grateful for your leadership, both in the class and outside of class. And we just really want to thank you for your participation again this year. we truly couldn't do it without you. And lastly, I just want to acknowledge our partners that helped produce this event tonight. I want to thank the NASA Astrobiology Program, and specifically Mike Tolian for all of your work in helping to produce this tonight. And also just want to acknowledge that Blue Marble Space Institute of Science also helps to put this on through their support of the live stream. So thank you to Blue Marble, to NASA, the NASA Astrobiology Program, and especially to Mike T, since you're here with us for these several hours every year. Thank you so much. And with that, I'll hand it back to Mr. Michael.
Thank you, Mike. And I'd like to thank, Mike and Dave and Nikki, really all three of you for the time and the energy, not just during the school day and during the time that we meet, but outside of the school day, really all hours of the day, including weekends. You're always willing to go above and beyond, and we really appreciate that commitment that you guys showed to this. And also, Ranger Sweeney, I know that, with all the challenges that you guys have been facing up at the park with the COVID, just restraints and restrictions, along with wildfire challenges, and then on top of it, just staffing issues and everything else. I just know it's been a real challenge from time to time for you, but you've always just been extremely willing and able to jump in and help us out whenever you could. And so we really, really appreciate that, and look forward to continued time and experiences with you up at the park. And to the interns as well. You heard Mike kind of recognize you all, and I just want to take a moment and do the same. The second year interns, I can't really say enough at the mix that you guys provided this year. Just a real balance with how you approach things. Between the five of you, you really covered a lot of different ground and really worked with everybody, all the first year interns, myself, NASA scientists, really everybody. You did just do an amazing job of connecting with us all. And so great job there. The first year interns, I realized that you haven't really fully had a real high school science year yet, based with all the just obstacles and everything else. But you guys showed up and you had just an energy, a commitment to this, and always a willingness to do whatever we asked of you, even when we were trying to struggle and figure things out. And so that commitment that you showed is something that I wanted to acknowledge. And so thank you for all of that. And I think what we want to do next is, I believe Olivia wants to say a few words, and possibly somebody else. I'm not quite sure about that, but I'm leaving that open. And so the interns have a few words that they want to say. So Olivia, if you're ready, it is time.
All right. So as a class, we decided that a special thanks was in order for Nikki, Dave, and Mike for all their hard work and dedication for this program. So every intern has picked out a little gift from our community to give you guys the next time we see you, as a reminder of us and just this program, and just a big thank you from us all for you guys. Thank you.
Thank you, Olivia. And so we'll have that waiting for you all. I'm not sure. I mean, I'm sure your summer travels and stuff will bring you all through Red Bluff at some point, and so as you come up to Red Bluff, you can just stop in and we can get that for you. And if not, then we'll be more than happy to hold on to it when we see you next in the fall next year. So with all of that, I believe we are done. I don't have anything else I want to add, unless anyone else has something that we need to add to this. I think we're going to end it right there. So are we good to go? Yep. Okay. Well, thank you all for participating and spending a little bit of time with us tonight. And we will see you all again next year, right around now. Okay. Bye.